LDA is sort of primarily falls in the generative class. So let's try to see the detail of this model and try to understand the property of the model. So LDA is short for linear discriminant analysis, and this is to separate the sample distinct group by transforming a space that maximizes these two quantities. So this is sort of semantic meaning of the model. And in essence, we are going to do this. We are going to project the input data to a smaller dimension space. And on this space, things are easier to separate. So separate different classes with minimum error. So let's take a look at this example where we are going to talk about projection. And say this is your data. We can easily think of projecting all the data in one of the axes. So for example, if you project all the data to x-axis, where you can imagine projections like this. On the other hand, you can try to project all the data to y-axis as well. If you do so, well, your result become like this. From here, you can try to set a threshold where maybe over here, everything right to this border where things are identified as red. Everything before this borderline identified as blue. Well, we can make a rule like this. Here is the same, so where you can make a decision rule like this, red and blue. But apparently this is not the best that we can do. The thing is, well, here there are some noises. So well, if we find sort of better projection, we can achieve more accurate prediction. For example, you can draw this line and try to project all the data points, and this projection allow us to make a perfect prediction. So the goal in LDA is to try to find the projection like this. So again, well, we want to find a projection like this green line. And this is a good projection where this axis separates all the classes correctly. On the other hand, this purple line, this is an example of a poor projection. If you project all the data points on this single line, well, things are even harder to make classification. So we want to find this, not this. So we were talking about things only visually, but we're essentially summarizing it into two sentences. So we want to maximize the variance of the class mean. At the same time, we want to minimize the variances of the individual classes. Let's try to find out what this means. So we want to find the projection like this. And here, individual class variance. This is smaller compared to this pro projection. So individual class variance here is larger than here. So in terms of individual class variance, we want to minimize it. At the same time, we want to maximize the class means, where that is noted as SB. We want to put the distance between these two classes as far as possible. So we want to maximize the distance between two different classes. If you look at the distance between two classes, well, things are not really separable on this projection, where these two are sort of very close to each other. Well, maybe this diagram is more accurate. So imagine that you have a projection like this over here, where if you try to plot two histograms by class on this projection line, where things are kind of overlapping. And in this overlapping region, you need to make a prediction with risk. On the other hand, where say you have a projection line like this, and things are all projected on this line, then histogram will look like this. And obviously things are much easier to separate. So then the goal is to find the projection like this. And we can summarize our discussion in this way, where eventually we want to find a projection like this. And W over here, it is the project function or projection matrix. Well, we talked about two different quantity. One is between class separability. So we want to maximize the distance between two different classes. And within class variability, we want to minimize the class variance in each class. where we can put everything into one quantity by putting things in a fractional number or ratio. So we want to simply maximize this ratio. So between class best probability over within class variability. And to quantify what we have discussed, where we want to maximize some function and between class separability, well, again, this can be interpreted as the distance between class number 1 and class number 0. And it is divided by the sum of variance from class number 0 and variance of class number 1. So our error function that is quantified as this, and we want to maximize this. Here, this head, where this is the mean and variance from the projection space. So this is different from the data from the original space. So from now on, we are talking about two different space. One is projection space and original space. In the projection space, we quantify things with the head. In the original space, we do the corresponding concept without head. So given that, let's move on. So these two are more precise description about the projection. So the mean on the projection space can be defined in this way. So you want to collect summation from one of the class, and that is divided by the number of instances from the class. And we are measuring WTX, that is the quantity from the projected space. And eventually that is equivalent to the mean from the original space projected to the projection space. A variance is described in the similar way. So basically variance is the projected value subtracted by the mean in the same space, projected value, mean, and you are basically taking the square. And that is equivalent to where put W outside of the parenthesis, and difference between each instance and mean, and difference between each instance and mean, and W is getting outside. So W from here comes outside, W gets outside because we have transpose here. And eventually we can write things down in this way. So W transpose variance from the original space and W. So it may take some time to follow, so well, you have to review the content to understand. I'm trying to explain the high-level motivation and mechanism of the derivation process. So we are talking about two quantity, one is within class scalar or within class variance. So for this, we want to minimize. And we also talk about between class scalar, we want to maximize. So to write things down again, large S0, that is equivalent to small s0 square, and this is small s1 square, where large 0 is basically variance of class 0 in the original space. The second one is the same, so variance of class 1 in the original space. And we want to maximize this, so where we want to take the sum, and eventually we want to minimize this quantity SW. And between class scalar, where that is measuring the difference between two different classes. So that is simply measured by comparing two mean vector. So again, well, this is to minimize, and this is to maximize. So well, this is the difference between M0 and M1, so mean vector. So we are trying to analyze these two quantity in the original space. So this is what we have done on this slide. And we are talking about things in the projection space. So next step is to quantify the same concept in the projection space based on what we have defined. So let's move on to the projected space. So in the projection space, we write down the same quantity JW, but we are talking things in the projected term. So the projected mean, where M hat, and projected variance, so S hat, where they can be written down in this way. So where everything is the same. So we want to measure the difference between the mean and measure the variance from each different classes. And we made the same ratio. And to tell you the conclusion first, where things are rewritten in this simple form. So WT, SB, WT, SW. And next two bullets is showing how you derive WT, SBW and WT, SWW, where based on the original mean vector and variance. So let's look at the numerator first, where this is to maximize. You want to maximize the distance between two mean, and this is the square. So initially you can write things down in this way, and these are the projections. So you can expand the projection in terms of W and the mean from the original space. And after that, you can associate W and take this out. So W is now here. And the second term over here, this is the transpose. So you can collect WT and it gets outside of the parentheses to this direction. So you have W because the transpose of the transpose is the original matrix. So if you write things down, you can come up with this multiplication using the mean vector from the original space. And in the previous slide, we have defined the SB to be the difference between the mean vector from the original space. So let's take it. So WT, SB, W. So this step should be clear. And let's move on to the variance side. So again, this is the variance from the projection space, and S square 0 hat, that is, let's go back to the previous slide, maybe here. We have the same expansion over here. So S0 square hat, that is the variance captured in the projected space, and things can be written down as the square term of the projection and the mean value. And the difference is squared, and if you expand it, WT in front of X, and this is WT M0. So WT gets collected and comes outside over here. The residue stays in the parentheses. Again, you have WT, and this is WT M0 from the original space. So you can collect these two and transpose this, so you can write W right after the parentheses. So eventually like this. So here is the conclusion. S0 square hat can be written down WT S0 square W. So using this expansion, S0 square hat comes over here. S1 square hat is right over here. And things are in common, so you can associate these two. So S0 square, S1 square, defined this in the previous slide as a total within class scalar. So using that, we can write things down in this way. So based on these two expansion, you can rewrite your goal function using simple multiplication of multiple vectors and matrix. And one of the caveat is while you are doing this, this is a linear combination, so eventually you can come up with a multiple W that satisfies this maximization. So in order to make this solution unique, we are adding one additional constraint. So given that, we can write things down in this way. We have derived the goal function in the projected space can be written down in simple multiplication and division. And given this quantity and the goal, we can rewrite this problem as maximize the numerator. And we came up with this constraint. So the denominator, the one in the bottom, should be equal to 1. So we have a maximization goal and a constraint. So this is optimization with a constraint. So we can bring one of the tool that we have studied earlier semester, Lagrangian multiplier method. So we can rewrite the above problem in terms of Lagrangian. So your goal to maximize together with an additional multiplier, together with the constraint. And to make the problem easier, we can adjust the problem one more time. So instead of maximizing the previous problem, well, let's put minus 1 over 2. And we put the negation in front of it. So instead of maximization, we can minimize the function to achieve the same goal. And since we put a coefficient in front of our goal function, we can adjust this constraint as well. And eventually we can write things down in this way. So if you take the derivative of this Lagrangian to get the minimum, so taking the derivative with respect to w that we want to find, you can come up with this simpler equation. And this simpler equation can be rewritten in this way, SVW lambda SWW. So in the previous slide, we derived this equation. So from Lagrangian, taking the derivative with respect to w and SCW lambda SWW. So I'm going to bring this up over here. So if you find the solution W star, well, that should satisfy this. And if you bring SW to the left-hand side, we can additionally define and simplify the term in this way. So S is now SW inverse SB. Given that, we can write things down in this way. And this is something very familiar to us. This is eigen decomposition. So eventually, we earlier have defined SW and SB from the original space. And if you have SW and SB, you can have a new matrix S. And what we want to eventually do is to find out eigenvector and eigenvalue of S. So where the full process is explaining eigendecomposition. But this eigendecomposition has a special meaning. So we are deriving a classifier. This special component here allows us to come up with a linear classifier. So that's the message. Well, here comes some additional note how to simplify the computation. So well, you can read through it. So the main message over here, where we wanted to find vector W. So this is the projection matrix or projection vector. And this projected space, we could do this. We could do this instead of doing this. And W that does this clear classification can be found by getting SW and SB from the original space. And SW inverse SB, if you do eigendecomposition on this matrix, you can get W that makes this projection. So that's the idea. But if you have a projection like this, the decision boundary can be drawn as a perpendicular line to this projection line. That's one side note. And the side note is well, sort of described on this prediction slide. So LDA eventually tried to find an axis projection. So it puts every data point on a single projection plane or projection line. And once W star, so the optimal W is obtained, you want to transform all the data to this axis. And from there, you can easily determine the class of the data. And in order to do that, you need to set a threshold. So above this point, everything is blue. Below this point, everything is red, something like that. And the decision rule can be described in this way. So well, your projection is larger than the threshold value, then well, maybe one of the class. If your projection smaller than some threshold value, then one of the class. So this rule is called as a Fisher classification rule. This is sort of all about linear discriminant analysis or LDA classifier. Well, LDA has been used in a number of examples. So first of all, well, although the derivation is quite complicated to you, I believe, But eventually, we can derive a simple W projection matrix or projection vector. And in terms of computation, it is really, really simple. So it has been used in face recognition, for example. So instead of looking at the original data, where you want to plug in your data and map it in some simpler space. So this is the projected image using the projection vector W. And based on the information in this projected image, you want to recognize this area in the picture is a face, something like that. And it also has been used in many medical diagnoses. So LDA can classify patient disease status or severity like mild, moderate, or severe. And customer identification can be done using LDA. So you can identify a group of customers who are going to be interested in certain product or who are going to buy the product, something like that.